notebook, we're going to be talking about vectors. And the way that we're going to conceive of vectors is simply that a vector is a column of numbers. We can think of a vector as related to a point, but we want to interpret it with an essentially geometric meaning. That is that it has an orientation. So we can think of the vector v as an arrow pointing from the origin to a point P. And so we have both the direction that this is pointing and the magnitude or the length of the vector. So we could write a vector either as a column of numbers or as a row of numbers. And I'm going to treat a vector as a column, and then we'll see how we can write a vector in terms of a row of numbers. So here I'm just going to import some stuff for plotting. And so I'm going to write a function for plotting vectors where, so you look at that if you're interested in the details. So here I'm going to take two vectors. One vector are the numbers 2 and 3, and the other are the numbers -1 and 5. So the first one I'm going to draw in red, and the second one I'm going to draw in blue. And so you can see this right here. So we have this going over 2 in x and up 3 in y, and the other one we're going -1 in x and +5 in y. So the elements of the vector are known as scalars, and for the example above, the elements of the red vector are the scalars 2 and 3. Okay, the dimension of a vector is the number of elements in the vector. So these are both vectors of dimension 2. And if the elements of the vector come from the real numbers, we would indicate the vector space, n space, as r to the n, where n is the dimensionality of the vectors. And as I said, our vectors are of dimension 2. Now, we can have vectors of arbitrary size, but we really can't visualize anything in more than 2 or 3 dimensions. But one thing we can do is we can project these vectors in higher dimensions into 2D or 3D space. But visualization is really another topic that we won't spend too much time on. So here's some example vectors. So v1 is a vector with elements 2 and -5, and the dimension of this vector is 2. Okay, v2, another two-dimensional vector with elements 7 and 9. Here, v3, we have a three-dimensional vector with elements -3, 4, and 5. And v4 is a three-dimensional vector with elements 3, -7, and 2. So here, just plotting some other vectors. Visualizing vectors in 3D space is a little more complicated. Matplotlib has a 3D plotting tool. In the notebooks, we can't make this interactive, and so it's not the easiest tool to visualize things with. But here's two vectors drawn in 3-dimensional space. Okay, if I wanted to depict a vector as a row of numbers, as essentially as we've done in these plots, we can think of a row as just a transpose of a vector. And so if I take v3 and write it as v3 superscript t, then that's going to become this row vector with elements 3, 4, and 5. So vectors are equal when every corresponding element of the vectors are equal. That is, the ith element in vector A corresponds to the ith element in vector B. So here's a function in Python that will check whether two vectors are equal. So the first thing is that we can conclude that vectors can only be equal if they have the same dimensionality, the same dimension, which we can check with the length function of Python. So I'm taking in two vectors, and I check their length. If they're not of equal length, then I raise a value error. The next thing I do is I loop through the elements of the list, and I check if element I in V1 is equal to element I in V2. As soon as I encounter a case where that's false, then I return false, because it doesn't matter what any of the subsequent elements are. All the elements need to be equal in order for the vectors to be equal. If I go through the entire all elements of the vector and I haven't returned false, then I can return true, because I've confirmed equality for every element in the array. So here we're checking equality of the vectors 1, 3, 5, 1, 3, 5. That's true. The vector -2 and 4 and -2 is not equal. And if I check equality between the vectors 1, 3, 5 and -2, 4, I get a value error because they're not of the same dimensions. Okay, so what are some of the common operations on vectors that we might do? So first off, we can do vector addition. So vector addition is defined by adding point by point the elements of the vector. And geometrically, this is equivalent to adding the vectors tip to base, which I'll illustrate in a figure in a second. So if I have a vector A with elements 2 and -4, and a vector B with elements 1 and 3, I add them element by element. So I'd have 2 plus 1 is 3, and -4 plus 3 is -1. And here's a function that is going to do that in Python. And let's draw this and see what this looks like. So I'm drawing my first vector in green. So this vector is let me pause there. Well, okay, so I'm drawing the first vector in green. And then I take my second vector, which I draw in blue, and I take its tail and put it on the tip of the green vector. And then where that now points to, I draw in red, and that's the value of the addition of those two vectors. Okay, so that's vector addition. I can also do scalar multiplication. And in scalar multiplication, I take some scalar value alpha and multiply it with, when I multiply a scalar with a vector, this is interpreted as multiplying every element in B by that value A. And so we're not changing the direction of the vector. Well, we can flip it if alpha is less than 0, but we're stretching or compressing it. So a vector defined along a line, so if I take this red vector and multiply it by some alpha, the new vector is going to lie along that line. It may go in the opposite direction, but it stays in that line. So here, given a vector B as elements 1 and 4, and a scalar beta, 2, so 2 times the vector 1, 4 is 2 times 1 and 2 times 4, resulting in a vector with elements 2 and 8. And here, I'm doing the same thing, where I have my original vector, and then I can scale it. And depending on the value that I'm scaling it by, so I have my original vector 1 and 4, which is drawn in black, and then plotting that same vector multiplied by 2, which is the red line, and I'm taking that, finally, taking that vector 1 and 4 and scaling it by -1.5, and then that becomes our green line. So you can see that as we stretch it or flip it, we're staying along the same line in the two-dimensional plane. Okay, we can add vectors together. and this is referred to as linear combinations. So I'm going to take three vectors, v1, v2, and v3, which I'm defining here. They're all of dimensions 3. And I'm going to multiply. So I'm going to do this linear combination of alpha times v1 plus beta times v2 plus gamma times v3. So I take my first vector, 2 minus 1 minus 4, multiply it by 2, 0, and then gamma is -1, so plus -1 times 1, 1, 3. So if I add up my elements, I got 3, -2, plus 3 would be 1, minus 1 is 0. And here we have -4 times 2 is 8, -8, plus 3 times 0 is still -8, plus -1 times 3, we get -11. And here's another Python function to do the addition of arbitrary number of vectors together. Okay, so here's an example computing the linear combination written out above, v1, v2, and v3. Let me fix my spelling error right here. So, and this is, so my v1 is 2, -1, 4, v2 is 0, 1, 0, and v3 is 1, 1, 3, which we have right here. I've defined this function vector addition, and what I'm going to do is I'm going to pass two of the arguments, the results of the scalar multiplication of my first vector, which I have stored in vs0, by the scalar 2, my second vector, vs1, multiplied by the scalar 3, and my third vector multiplied by the scalar -1. And we can look at this in the projection in the 2D plane, at which you see I'm pulling out the xy, the first two positions of the vector here with slicing. Okay, two remaining ideas that will be important for our future applications are the concept of a vector norm and the concept of a dot product. So a vector norm can be thought of as a measure of the magnitude or the size of the vector. And the most common norm would be referred to as the Euclidean norm or the L2 norm. And the way this is computed, it would be signified by these double vertical bars with the vector name inside, is we take every element in our vector, we square it, we sum those all up, and then we take the square root. And you can see this is where the concept of the p comes in. So 2, our L2 norm, you see we're raising every element to the power of 2, and then we're taking the root, which we can think of as a power of 1 over 2. So that is a norm. It's our measure of the magnitude of the vector. We can create a unit vector by taking a vector and dividing it by its norm. And so here if I have a vector u, if I take that vector, and so a division is just a multiplication, so this is a scalar, stretching, compressing of the vector, divided by the magnitude. Then when I take the norm of this new vector, u star, it'll have a norm of 1. So here's a function to compute the Euclidean norm of a vector. And so my vector 1, 3, 4 has a Euclidean norm, a L2 norm of 5.1. My vector 1, 0, 0, not surprisingly, has a norm of 1. And my vector 1 over the square root of 2 and minus 1 over negative 1 over the square root of 2 has a magnitude of 1. Okay, the next concept that will be important to us is a dot product. This is also referred to as an inner product, and this will be a very important idea for us to understand. So a dot product is obtained by multiplying corresponding elements of two vectors and then summing the product. So if I have a vector u and a vector v, I iterate over every element, which I have is this I equals 0 to n minus 1, and I take u of I times v of I, and I sum those together. And this, it would be written as u dot v. So the dot product, or inner product, measures how parallel two vectors are. So if the inner products of the two vectors is 0, then they are orthogonal. They're pointing in at a 90-degree angle to each other. And we can use this concept of the dot product to actually measure the angle between two vectors. And if we step through the geometry, we can get that the cosine of phi being the angle between u and v, is equal to the dot product of u and v divided by the norms of u and v. So this dot product is going to be a vector property that we're going to use to find the similarity between two vectors. And here's a function to compute the dot product of two numbers and plotting two vectors, and then we're plotting three vectors here and computing the dot products between them. There's also an idea of a cross product, which we won't be dealing with, and there are inequality rules that we sometimes might be able to exploit in our analysis of vector data.